Hello students, and welcome again to my channel. My name is Mr. Meshak Ngige, and welcome to eMaths with Meshak Ngige. So kindly, if you have not subscribed, kindly subscribe, share, and also comment to your friends and colleagues that these lessons may be helpful unto them. Now today we're going to be checking a series of revision, and we're going to be checking a particular part of complex analysis. For those who are doing module 3 mathematics, this is your video. So kindly remember to subscribe, share, and also comment as we dive into the lesson. Thank you, and now let's jump right in. So we check our first question, and it says determine whether f of z, which is given by exponent of 3z, is an analytic. Are we together? So solution. So our solution, we check the question. Now, so your function is f of z given by exponent of 3z. So we have to express our exponent 3z into another form, which basically is in terms of polar form. Are we together? So z, remember, the reason for doing that is because our value our value of z is different. Z is given by x plus y, yj. Together. So this one now will just give us f of z is the same as saying exponent of 3, then we have x plus yj. When you open this bracket, you have e 3x plus 3y 3yj. Now, from the laws of indices, when you have, we'll use this law, am multiplied by an is the same as saying am plus n. That means the bases are the same, but our powers are different. So what do you do? It is the same as saying you add the powers and you put only one single base. And if you check our exponent, it is written in this form. Right, together, it is written in this particular form. So we can split this into this form. Right, together, our exponent is in the second form, so we split it to become in this form. So what will be our base? The exponent. Okay, so we shall have, so e of 3x plus 3yj will be given by exponent 3x, then exponent 3yj. Now this part here, remember, how do you change polar from polar to exponent and exponent to polar? We know something, that when you have r and theta, this is in polar form, which is basically written by in full. Remember, this is the short form for polar form. In full, this one is written as r into bracket cos of theta plus j sine of theta. These are from introduction to complex numbers. Introduction to complex numbers figures this one out. And now this one again can also be written in terms of exponential form. An exponential form for this part will be written by r exponent. Then we shall have the value that we have here, which is the angle. Are you together? Then we have the what? We have the j. So we have r exponent, then theta j. So if this is our polar form, and it can be changed to exponential form of complex numbers, therefore we can see that this part of this function is expressed in terms of polar form of complex numbers. But now our value theta here, any value before the j represents your angle. Are we together? So if you have theta here, what do we have here? We have 3y. Are we together? And since this one is appearing in this form, we can assume now this one is our what? Our r. Are we together? But not necessarily. So we have, therefore, so in this form, so we can now change this form to come to polar form, and it will be represented in this form. Are we together? So exponent of 3x, exponent of 3yj can be written as exponent 3x into bracket. We now change this part. Are we together? This part is represented by this part, so we shall write cos. But what is our angle? Our angle is 3y plus j sine. What is our angle again? 3y. Wow. You can see the process. So this becomes this. Now we can at this point now, we can split this into real and imaginary. So we can just open our bracket and we shall just have exponent of 3x, then cos of 3y, plus exponent of 3x, sine of 3y. Then you can put that one together, then you put the what? We put the j outside. Are we together? So we have that part and that part. So what is our u part? So our u in that case, which is the real, our u in terms of x and y will be given by exponent 3x cosine of 3y. What is our v in terms of x and y? Will be exponent 3x, then we have the what? Sine of 3y. Remember that the one without the j is the real part, and the one with the j is the imaginary part. Are we together? Yes. Now, so we want to prove that this is analytic. So that is simple, because we just have to find these two conditions, that du dx should be the same as dv dy, and dv dx should be the same as negative du dy. And remember, all these are partial derivatives. So those ones are just called cal d. The d is cal, but we are just stating it in that form. So we have these two conditions for a function to be analytic. So that means we have to differentiate a function of u with respect to x and also with respect to y, and also a function of v with respect to x and with respect to y. So let's start with the first one, du dx. So we differentiate our function with respect to x. Are we together? So which function has the x? It is only the exponent function. Are we together? So we just differentiate the exponent, treating cos of 3y as a constant. That is what we do in partial derivatives. Okay, so if we differentiate exponent of 3x, we just have 3 exponent of 3x. Then this one is a constant, so we just leave it the way it is. Then we have du, then with respect to y. Now we differentiate this function again, but now with respect to y. When you differentiate cos, you get negative sine. Are we together? So we have negative, our exponent remains, there's a constant. So when you differentiate cos, you get negative of sine, but now you always remove the what? The constant outside. So we have negative 3 exponent 3x, then this one becomes what? Sine of 3y. Remember, this negative is whatever we are saying, that when you differentiate cos, you get negative sign. Now let's come to the second, dv dx. Differentiate this function again with respect to x, and again you drop 3 exponent 3x. Sine of 3y is a constant, so it remains to be a constant. Then you come to dv dy. All right. So again, differentiate this one with respect to y. So the function with y is the sine. When you differentiate sine, you get positive cos. So you just have what? There is no change of sign. So you just have 3. So you remove the 3. The exponent of 3x remains. Are we together? Then this one changes to become what? Changes to become cosine of 3y. Now let's just check the two conditions. Have your two conditions been met? So what is your du dx? 3 exponent 3x cos of 3y should be equals to, what is your dv dy? 3 exponent 3x cosine of 3y. So the first condition has been met. Then you go to the second, dv dx, which is 3 exponent 3x sine of 3y should be the same as negative du dy. Du dy is this. So we have negative 3 exponent 3x sine of 3y. But a negative multiplied by a negative gives you what? A positive. So therefore we have 3 exponent 3x sine of 3y, and whatever we have on this side is whatever we have on the left hand side. So therefore your two conditions have been met. Hence we say, hence exponent of 3z is what? Is analytic. So that is how you determine. So the important part here when you're finding derivative of before you even find the derivative of the function is to express your exponent function in terms of polar form by the end of the day. Are you together? Yes, you express it as a polar form. Then from there, get the real, get the imaginary, then differentiate from that point. So thank you. Let's now check our second example.